So today we're doing lecture 0. So this is really before we get into what is the true content of the course. But what we're trying to do today is to make sure that as we get into the true content of the course, I will probably start using various terminology that if I haven't talked about it before, it might start confusing some folks. Some of it, though, is probably going to be very familiar to a lot of you, but we'll at least get sort of our operating definitions of some of these terms as well as talk about them a little bit. And that way, hopefully, as we dive right into the content of the course, we won't get stuck on some of these terms or so the other thing that we can get stuck on sometimes is what the symbols look like as you draw things, in a schematic or on a circuit diagram. If you don't know what certain things mean, it can kind of get you stuck. And so I'm going to try to do a decent job right now of getting us started on that side of things. So the place we probably need to start is with the definition of something that's called a circuit element. Okay. As we develop these circuits, essentially what they are is a connected group of these little pieces, right? And those pieces, the general term for those pieces is a circuit element, okay? They're the building blocks of these electrical networks. An element is a little bit different than a component in that a component is typically something that you actually can go and pick off of a shelf somewhere, right? You can find a resistor and plug it into your circuit, or you can find an inductor and plug it into your circuit. A circuit element, on the other hand, are somewhat idealized typically, right? So if I need let's say an inductor, right? On my diagram, I can draw an inductor and I can assume ideal behavior of that circuit element, right? Even though I might not be able to go pick one of those off of a shelf. So the one I pick off of a shelf is a component. The one that I put on my circuit diagram is an element. Does that make sense? So there can be a little bit of difference between what is truly actually available as these circuit elements, and so one way of kind of distinguishing those is with components versus elements. Also, the idea of sources, right? Voltage sources or current sources are things that we are going to work with in this class. Turns out neither of those truly exist in the real world. So that's an example of they can be circuit elements on our diagrams, but we can't necessarily go and pick one of those off of a shelf. So anyway, let me just kind of show you some of the symbols that are going to exist for some of these circuit elements. A resistor, we are going to represent that with a little squiggly line like this with hard edges, okay? That's a resistor. An inductor is represented by this sort of little coily kind of a diagram like this, or occasionally sometimes people will draw that instead of looking truly coil-like that, they will draw it like this, kind of like a few humps, okay? So that's what an inductor looks like on a circuit diagram. By the way, when we do the lab, you will also get to get your hands on some physical versions of these so that you know what they look and feel like. A capacitor typically involves having two parallel lines with a couple of terminals that come off of it like that. We're going to talk about a few different kinds of sources. The two symbols that we typically see for sources usually either involve like a circle with a couple of terminals coming off of it, or a little diamond shape with a couple of terminals coming off of it. For voltage sources, what we typically do is we will show the voltage polarity of those with a little plus or minus. Current sources look very similar as far as the diagrams that we draw. They have a little arrow that points the direction that the current is said to be flowing in that device. And we can also have another type, and I will get into the details of when you would use one of these symbols versus the other, but these are a couple of examples of what these things might look like. Today, we're not getting into the details of any of these circuit elements, and so what I'm going to do today is talk about circuits in general where I don't have to be specific about the specific elements that are in the circuit. And so what I will do is I'll actually say a way that we can generalize that is just put a little box there, right? And say that is just a generalized circuit element. Okay? And that's how I'm going to talk about it today. Now, let me say this. You might notice something about every single one of these examples of a circuit element that I put up on my page. What do you notice about them? Anything interesting? Okay, they have wires that come out. Do they all have the same number of wires coming out? Okay. Yeah. How many? 2. All of these different elements that I've put up here on my page are examples of what are called 2-terminal circuit elements. Okay? So that is the most common thing that we will say, or that we will see is, and I'll put that up here, most common 2-terminal elements. Okay? Vast majority of what we do in here is going to be working with 2-terminal elements. Now, that means, that at least sounds like, there will be at least one thing that is not a 2-terminal element. So I'll go ahead and throw that one up here too, just so that you have something to, I guess, contrast it against. What if I drew something like this? You know what that is? Some of you may have seen it before. This is a symbol for something that's called an operational amplifier, or that is often abbreviated as an op-amp. Okay? What do you notice about that one? That one has 3 terminals, right? So this is one example of an element that is not a 2-terminal element. Only reason I put that up there is not so that we're going to try to deal with it right now, but I just wanted you to see one other example that not every circuit element has to have 2 terminals. It's just that the ones we work with in this course are vastly going to be 2-terminal circuit elements. Okay? So that's kind of our starting point. The next thing I want to define is the concept of a path. All right? Specifically, when we talk about these paths, we're talking about a path that electrical current is expected to be able to flow on. Okay? Now, this gets a little tricky when you're out in the real world, because just about anything can become a conductor of electrical current if you have enough voltage. Okay? So, but it's easy enough in general cases for us to look at things and go, I think it looks like there's a path where current could go on a wire or on a circuit element. Speaking of which, what would a wire be depicted as on a circuit diagram? Okay, anytime you see on a circuit diagram just lines, those are expected to be wires. Okay, the other thing that we're going to do in here is when you see wires on a circuit diagram, we are going to assume that they have 0 resistance, that they will allow current to flow unimpeded on those wires. Real wires don't really behave that way, but we are going to assume that they behave that way, or at least are close enough to behaving that way that we can model them that way. Okay? I already talked about the general circuit element, so I'll draw that over here as well. A circuit element also represents, in most cases, a path along which current can flow. Okay? Now, here's maybe a more tricky one. A switch. Here's a circuit diagram for a switch. Okay? Now, what does that look like? It looks like a broken wire, okay? And it looks that way on purpose because that's the job of a switch, is to either connect your wires up or not, right? And so when it is in the state that's shown right here, that is known as an open switch, which makes an open circuit right there. It means there's no path for current to go. If you close it, right, if you actually take that little switch and connect it up, that is considered to be a closed switch. You don't usually see them depicted that way, where it's closed, but anyway, this is kind of how a switch works. And so the idea there is you are either creating a path when the switch is closed, or you are interrupting the path and breaking the path when it is open. Okay? Good so far? All right, let's get into the next group of things here. All right, we are talking about systems where we're going to have multiple circuit elements that connect with other circuit elements. And so the place where these connections occur are called nodes. All right? So what I want to do first is draw for you the most simple electrical network. Okay? Here is the most simple electrical network. Circuit element, bam. Okay? That is the most simple electrical network. It has one connection, okay? And that connection is right here on this node, right? That is a point of interconnection between these two circuit elements, okay? Now, we can have more than that, too. Like I could, matter of fact, let me just copy and paste this right here. You know, I can show this as another example of a node where several circuit elements come in and actually all connect there at that location. All right? Now, I have a couple of sort of nitty-gritty things that I want to talk through because there is some difference about how some people depict circuits and other people depict circuits, okay? And it has to do with where do connections actually occur in a circuit diagram that you have drawn. I am going to be doing the vast majority of my circuit drawings that I do in here by hand on my sheet of paper. And what I'm about to show you is what I think is the easiest way, at least for me, to depict certain types of connections. Some of them are unambiguous, like this one right here that I already have up there, A, B, and C. Where do those connect? I mean, totally unambiguous, right? They all connect right here, right? Now, where it gets more tricky is what if I add an element D and I show it like this? Okay, and let's say that, let's say that this is part of a bigger circuit, so it goes on and it goes other places. We're just zoomed in on one little spot on this circuit, right? How do you interpret this? Just tell me what you think. Like, what does that look like it would be? Okay, it looks to me like A, B, C, and D all connect at that point right there in the middle, right? Is that what it looks like to you? Yeah. So that's how I typically, interpret a drawing that looks like this, particularly if it's a drawing that is done by hand. Okay? Now, what if I wanted to depict something where B connects to C and A connects to D, but they don't connect to each other? Okay? That is what I typically do when I draw these circuits. He says you could show a hump in the wire, right? So you could kind of have an alternate way of showing this same type of a system where you might show one of the wires that connects straight across between the two, like B and C right there. And then for the other one, you show a little hop, right? It shows hopping over that wire and going to these other ones. That is not an uncommon way to do this. But I will say there is another standard out there as well for how to depict these things, and it involves drawing a dot. Okay? The other standard, the other standard that doesn't use the hump, right? If you saw a connection diagram that looked like this without a dot drawn where these things connect right there, how would you interpret it? You actually interpreted that B connects to C, and A connects to D, but they don't connect to each other on that intersection. In order to make them connect, you would want to draw a dot. And then that says they're connected right there. Now, I don't really make strong use of dots like that when I draw diagrams, but I want you to be aware that there are a few sort of dissimilarities that happen between the way some people draw circuits and the way other people draw circuits, okay? And so sometimes it's important for you to kind of go back and figure out what standard is being used for how the circuits are drawn. I think the clearest way for me to do things in class with the least amount of explanation is that if wires look like they touch, they connect, right? And I'll try to do stuff like this where I hop over like this to try to communicate, no, they don't connect. And hopefully I think that's the clearest way for me to communicate things with the least amount of overhead. But again, here I am spending overhead trying to explain it anyway, all right? So All right, that's it for that. The other thing that I want to mention is that once you have assumed that your wires are zero resistance, then it doesn't really matter what shape a node is going to be, right? I showed this example of where we've got this interconnection point between these few elements. It would not be different for me to draw this figure where, let's say I showed one wire and I have one circuit element coming off down here, and it doesn't really matter which one, honestly. And let's say I have another circuit element coming off over here. I'll call that one B. Let's say I have another one coming off up here, and I call that one A. And then let's say I have one more that comes off and goes down here, and I'll call that one, which one am I missing? D. Okay? What I just drew up there is not actually different than the one that I had to the left of it, okay, in terms of how it will functionally behave. It's not different. So how you draw a node is not always, there's a lot of times a lot of leeway about how you will draw a node, because the main thing is you have to show it connecting to the correct elements. But how it does that connecting, it doesn't really matter. Okay, with me so far? All right, the next bit of terminology I want to bring out is something that's called a branch. Okay? A branch is a single path between two nodes of a circuit. All right? And a couple points about this. There can be multiple paths between two nodes, and there can also be multiple elements within a path. Okay? So let me actually ask you here. Let me number some things. Let me number this node over here 1, and I'll draw some color on it. Let's say that's my node number 1. Down here, let's say I've got node number 2 down there. Okay, and then I got node number 3 up here. Okay, now do I have any other nodes? This is a tricky question. So technically, yes, I do. Where? Okay, right there between C and D. That is also a node. It's just not that interesting of a node. Why not? Precisely for the reason that I'm about to talk about, and that is, it is all part of a single branch, right? If you look at what connects across from 1 to 3, right, there is a single path for current to flow from 1 to 3. It has to go through both C and D, right, to go from 1 to 3, but there's no other place for it to go. There's just one path for it to go between those two locations. And for that reason, I would identify that right there as a branch of this circuit. Does that make sense? Because it's a place that connects between node 1 and node 3, and it gives you a single path where current can go across that location. Now, what about between 1 and 2? How many branches do I have between 1 and 2? I've got 2, right? One that goes across element A and one that goes across element B. There's 2 different paths for me to get from node 1 to node 2. What about for node 3 to node 2? 3 of them, right? E, F, and G. Could I make any one of those, E, F, or G? Could I add, let's say, another element in that line and still have just one branch? Yeah, I could. Like I could put another circuit element like right here and call that H or something like that. That would still just be one branch. The combo of H and E would be one branch for you to go from 3 to 2. Okay? With me on that? So if we talk about branches, that's what we mean. All right. Now, related to that are these terms series and parallel. All right? If you have 2 or more elements that are connected along essentially one branch, like one long chain of elements, they're connected end to end to end to end to make a chain of elements, then it is said that those elements are connected in series. Okay? Now, is there something I could do to wreck that status of it being in series? Probably so, right? What if I did this? What if I put another element right here? Are A, B, and C still in series? They are no longer in series. Are A and B still in series? They are, okay? So you have to be careful of this and say there has to be an exclusive path through all of those elements that are chained together end to end to end in order for them to actually be in series. Yes, sir?
Could you say that A and B are in series with C and D?
A and B would be in series with the combination of C and D, assuming they can be combined. That's a big assumption that we haven't gotten to yet, because these are general elements, right? Like, you can't necessarily assume automatically that you're going to be able to combine, let's say, a voltage source with an inductor, right? Like, that would be a strong assumption that you might have there, that you might be able to combine those together. So if they are combinable, then what you're saying is an accurate statement. They just might not be. Okay, so I'm going to erase those to not make it ambiguous. That was a what-if question. Two or more elements are said to be in parallel if they connect across the same two nodes, right? The same pair of nodes, if all of the elements connect across the same pair of nodes. And the easiest way, in my opinion, to visualize that is to color the nodes, right? So we have those two nodes. A and B are two-terminal elements, which, by the way, I didn't really make a big deal of that, but I did write it as a note up here. Both series and parallel formulations like this presume that the elements that you are dealing with are two-terminal elements. Okay? So anyway, here we have A and B both connected across the same pair of nodes. What if I was to add another branch of this circuit and put an element C over here like this? Is C in parallel with A and B? How do you know that? Does it look like it's in parallel? Well, it kind of depends on how you draw it, right? How you draw it, though, is not the important thing. It is, what is the meaning of parallel? And the meaning is it's connected across the same pair of nodes. So what you want to do is you want to go in and say, well, that node really extends to there, and this node really extends around up to there. So is C also connected across the same pair of nodes as A and B? It is, and so C is also in parallel with A and B for this alternate circuit that I've just drawn. Okay? Now what happens if I come in here and change it up a little bit? What happens if I come in and add another element and I put it right there? Okay? What's in parallel now? Okay? A and B are in parallel with each other. I agree with that. Are they in parallel with C? No. Are they in parallel with D? No. How do we know that? Okay? I can continue this node out and I can see D is not connected across the same pair of nodes as A and B. Why not? Because I've now got this other node right here. Right? So C and D are not in parallel with each other. They are also not in parallel with A or B. Okay? Now, is there a relationship about how C and D might relate to each other with this alternate circuit I've just drawn? They are in series with each other. How do we know that? Okay? There is a single branch, a single exclusive path to go from yellow to green, right? As it goes through C and D, it doesn't have any other place to split off. If it goes over there towards C, it will go through D, right? So that tells me that C and D are in series with each other with that final kind of version of the circuit. Again, I'm going to erase that just because I don't want to leave any confusion about what I was saying. Those were some what-ifs, but this is definitely still three elements there that are all in parallel with each other. And again, the key point is you want to look at the nodes across which all the elements connect. And if they connect across the same pair of nodes, then that means they're in parallel with each other. Okay? Now there's an even bigger way of kind of thinking about these circuits, and that is two networks are said to be schematically equivalent if they have the same nodes and branches. Okay? So I just wrote for you a messy looking circuit up there, right? This thing right here. What if we wanted to make that cleaner looking? Could we do that? And if so, how would we do that? Yeah, I think that's a really good start, is to first, right now, it confuses our eyeballs, like where do all of these wires go, right? Even if you don't have an eye problem. All right, so what we want to do is we want to get in there and try to separate and say this is this node, and that kind of thing. And I've been doing this here, but I'll call it out specifically. As you do this, in my opinion, the easiest way to do it is to drop some kind of a highlighter on one of the wires and color in every direction until you hit an element, right? So I colored all the way I could go in that direction, but did I have any other places where it peeled off? Yeah, I had one over here, and that goes all the way there. Have I colored everything for that node now? Okay, I have. Now, let me go and color another one. I have this other node that goes from A to B, right there. It doesn't look like that one peeled off anywhere, so that might be all I need to do there. What else? Here I go from D over to B and up to C, and it looks like I have identified my 3 nodes. Okay? Now, is there an easier way to draw this, or kind of a cleaner way to draw this circuit? There is, and all you have to do is make sure you connect the same circuit elements across the same nodes. And then you have an equivalent circuit, right? So what may be an easy way to do that? Okay. I heard someone say D and C on the end, so let's say I put C right here and maybe D over here. And those connect to what? D and C both connect across yellow and green, right? So let me go ahead and draw those on here, like actually color those in, yellow and green. And then from there, what do those connect to? Yellow also connects to A, so I can draw that on there, and that is not incorrect. What does A connect to? B, right? And what does the other side of B connect to? The combo of C and D. Now, what I have drawn is probably a lot less difficult for you to parse visually what's going on that circuit as opposed to the original one. But they are not different circuits, right? Both of them will behave exactly the same way. I've just drawn it in a way that is easier for me to deal with. The reason this works is that those 2 circuits are said to be schematically equivalent. Basically, they have the same nodes and the same branches, so they work exactly the same. Okay? Questions yet? All right, let's go on to another set of things. A loop is any path. Remember, we already defined a path as a place where current can go. A loop is any path that returns to its starting point while not passing through any node more than once. Okay? And if you have something like that, if you have a path like that, that is called a closed path. Okay? And it makes this thing that's called a loop. Let's identify some loops on this circuit that I have right over here. Okay? Like what? A to B to C, around back to A. I didn't touch any one of my nodes more than once, right? So that would be one of my loops. Are there any other loops? Okay. I could go from A to B, around to D, and back to here. I went all the way around, didn't touch any of my nodes more than once, so that would also be a loop. Are there any other loops? Okay. I also have a little loop right over here, right? I can go up and around through C and through D, and I get back to my starting point, not touching any node more than once. Okay? And I think for that little diagram right there, that would be all of my loops that I would have in that figure. Okay? Now, this is an interesting distinction, and it's one that I will just be honest with you, I am not always the best at making sure when I'm in the middle of a problem and speaking about the problem, I sometimes use terminology that I maybe shouldn't. Okay? and it is this. The word network and the word circuit are both very similar to each other with a major difference. And the major difference is this. For something to truly be a circuit, it has to have at least one loop in it. There has to be a closed path for current to flow on, or else it is not truly a circuit. The better term to use if you have a system that's set up that way is actually a network. A network is a more general term than circuit because a network is not required to have closed paths. Okay? So all circuits are examples of networks, but not all networks are circuits. Does that make sense? So anyway, this is an example of something that I probably should call a network, right? What would it take for me to call this a circuit? Now it's a circuit, right? That wouldn't be the only. I could also do this, right? I could show another element over here. Let me say I call that element D, and I hook it up in there like that. That's now a circuit, right? The only thing that makes it not a circuit in the other case is that you don't have any closed paths in that case. And so a better word to use in that case would be network. And the truth is you can use the word network for circuits also, right? Because a circuit is a network. It's just one that happens to have one closed path at least. All right, now here's an interesting one that we won't talk about a whole lot more until several class meetings from now, but that is the word mesh. A mesh is a certain type of loop. It is a loop that doesn't contain any loops inside of it. Okay, so if you look back up at our first definition of loop up here, and you look at the green loop, inside the green loop, you will see that we had the blue loop and the red loop, right? So the green loop up there is a loop, but it would not be a mesh, right? The blue loop is a mesh, and the red loop is a mesh, because neither of those contain another loop inside of it. Does that make sense? So down here, where would my meshes be on this circuit that I have down lower down here? Let's say I start up, maybe I start down here. I could go through A and down through B and over to D. That would be one of my meshes, right? What about on this one? Maybe I could start here. I could go around. If a loop was identified like that, that would be a mesh, right? What else? Another one right there. Now, are there any other loops in that bottom circuit? There's plenty of other loops, but those are the only meshes in that circuit. Okay, does that make sense? So it's important to be able to identify where you might have meshes versus where you might have loops. We're going to do a technique a little bit later in the course called mesh analysis, and as you might expect, you have to be able to identify your meshes in order to be able to do a technique called mesh analysis. So, and that actually concludes the important terminology that I wanted to talk through today. So I will entertain any questions if there are any. All right. Don't forget about getting your lab kits. And other than that, I'll see you on Monday. We'll do lab 1 then.